What has scored these grooves or striations on these rocks in New York's Central Park? How did these brown cobbles, formed of rock from Norway, come to be amongst the local flints used to build this church in England? What agent formed U-shaped valleys here in Scotland? They're all evidence of the action of glaciers. Glaciers form where conditions are humid and cold enough to permit the accumulation of snow from year to year. Today, such climatic conditions only occur at higher latitudes towards the poles or in mountainous regions at lower latitudes, such as here in the Swiss Alps, where the drop in temperature with increasing altitude produces the necessary conditions for substantial snowfall. Every winter, the Alps are blanketed in snow, yet only in these higher regions does the snow persist in summer. Here, the combination of high snowfall and low average temperatures leads to annual accumulation of snow. These regions above the permanent snowline are the accumulation zones for glaciers. Snow packs into basins to form vast volumes of ice, which are the source of the glacier. Under the enormous pressure from above, the ice becomes plastic and begins to flow. Pressure also makes the ice in contact with the bedrock melt, allowing the glacier to slide as well as flow. Moving a few centimeters a day, the ice takes the path of least resistance, usually channeling into existing valleys to form remarkable rivers of ice. Such glaciers are known as valley glaciers, and this, the Aletsch Glacier, is 15 miles long. The continual supply of ice from the accumulation zone allows the valley glacier to flow well below the permanent snowline. Here, in the ablation zone of the glacier, evaporation and melting are slowly whittling it away. Even though the ice is plastic at depth, its surface layers are still brittle, and where the flow of the ice beneath puts stress on the surface, it fractures to form crevasses up to 100 feet deep. Nowhere is this rending of the brittle surface more spectacular than where the glacier cascades over a step in the bedrock, forming an ice fall. Steeper faces of the mountain where snow cannot rest are exposed to wide temperature fluctuations and severe freeze-thaw weathering. Huge quantities of frost-shattered rock debris slide down the faces onto the glacier's edge. These strips of debris are known as lateral moraine, and the glacier acts like a conveyor belt, slowly but relentlessly transporting it away. The dark lines, like road markings, are also moraines. Where the lateral moraines of two converging glaciers meet, they combine to form medial moraine, giving the valley glacier the appearance of being divided into neat lanes. Ultimately, valley glaciers terminate in a snout. The glacier's snout is formed where the average rate of evaporation and melting equals the rate of supply of ice. most of the rock debris that the glacier has been carrying is dumped around the snout as terminal moraine. Debris deposited as the snout melts back in warmer periods is bulldozed into ridges as the snout advances further downhill in colder periods. Here, though broken through by meltwaters and crisscrossed by paths, the shape of the banks of terminal moraine clearly mirror the shape of the snout. The presence of several ridges of terminal moraine shows that once the snout was considerably larger and that now it's in a period of overall recession. It's clear that the surface of the glacier transports enormous amounts of debris. But closer inspection reveals that the ice itself is full of dark bands. Rock debris is carried within the ice, and it isn't just small stones. In places, it envelops large boulders. In some glaciers, meltwaters produce caves beneath the ice. Here you get a unique chance to see what's happening to the bedrock. It's smoothed, and notice the presence of striations like those we saw in New York Central Park. What's been happening? Dr. Jeff Bolton.
There's about 100 feet of glacier ice above this point. The ice is moving in this direction at about 2 centimeters a day, slipping over its bed. And you can see in the roof of the cave debris which has been ground by the glacier from the bed over which it's moved, which is now being transported forward. Contained within this basal debris layer, one occasionally meets quite large boulders. And these are the things which are largely responsible for grinding the glacier bed and producing striations on bedrock.
This projection of bedrock reveals yet another characteristic of the glacier's erosive action. The upflow surface has been rounded and streamlined by the grinding action, whereas the downflow end is jagged, where local freeze-thaw action has plucked at the rock. The scouring action of the valley glacier remolds the ancient river valley, removing valley spurs and generally straightening its course, producing the characteristic steep-sided, flat-bottomed, U-shaped profile that is such unmistakable evidence of the erosive action of a glacier. These ice-filled basins high above the main valley glacier are called cirques, and their very shape is a testimony to another variant of glacial erosion. The clue to the action is these crevasses close to the rock face. They're called bergschrunds. During the summer, the bergschrund permits water to reach the rock face. There, it seeps into fractures in the rock, and subsequent freeze-thaw action causes frost shattering and the incorporation of rock debris in the glacier's soul. Ice flow within the basin is a rotational movement, which results in the armored soul scouring a pronounced hollow, which later will form a small mountain lake. Cirque glaciers gnawing away at the mountain often join up so that the mountain is eaten away from two sides to form a sharp ridge known as an arête. The same process taking place from 3 or more sides leads to sharp peaks known as horns. This process has led to the unmistakable shape of one of the Alps' most famous peaks, the Matterhorn. These spectacular features are diagnostic of glacial erosion, but there are other means of diagnosis. As the glacier melts, it dumps everything it's carried. This ranges from fine rock flour, mud and gravel to huge boulders often much larger than a man. This whole range of totally unsorted debris is called glacial till. 10 miles down valley from the glacier's snout, A road cutting reveals a bank of glacial till, a sure sign that once the glacier filled the whole valley, but has since retreated. Here, carbonates have cemented the till, and it has weathered into fantastic spires. It's easy to be confident of such evidence of glaciation when the glacier's still nearby. But how well do these features pass the test of time?
2 to 3 million years ago, the climate here in the Colorado Rockies, as indeed over most of the world, began to get colder and wetter. And in mountains such as these, glaciers began to form. But the ice is now gone, but it left behind a tremendous amount of evidence of its presence. It's left behind cirques, which are amphitheater-like depressions. These basins were the areas in which the glacier formed and moved out to become powerful erosive agents. This is also the type of country in which we see arêtes. In many areas, several cirque basins merge to form the characteristic U-shaped valley, and in turn join a larger complex system. Indeed, some of the glaciers here were in the neighborhood of 13 to 15 miles long. The ice carried with it enormous quantities of debris. If we were to go down valley, down glacier, we should see evidence of glacial deposition in the ablation zone of the glacier. The valley below was almost completely occupied by glacial ice. The flat floor is flanked on either side by tree-covered ridges. These are lateral moraines. The two laterals swing across the valley to form the low, tree-covered ridge, which is actually the terminal or end moraine. The moraines in here were about 500 feet thick. Now the moraines and the shape of the valley allow us to gain an approximation of the thickness of the ice, which turns out to be in the neighborhood of 1,000 to 1,500 feet thick. Imagine what this country must have looked like when the glacier was in this valley. And as big as a valley glacier like this may seem to have been, it was small compared to the vast continental ice sheets that spread out over the lowlands, covering millions of square miles of North America and Northern Europe.
The last ice age, the Quaternary Ice Age, started over 1 million years ago. Since this time, the ice has advanced, then retreated several times, the most recent advance being between 70,000 and 10,000 years ago. During glacial advances, huge ice caps formed, burying mountains in ice over 5,000 feet thick. The ice flowed out of these centers of accumulation to form gigantic ice sheets extending hundreds of miles onto the lowlands to form continuous ice fronts thousands of miles long. As the ice sheets melted, they left enormous tracts of till with its characteristic humpy morainal topography. Evidence of the extent of the ice sheets comes from erratics, boulders left many hundreds of miles from their bedrock source. Lowland glaciation leaves its own characteristic features as the ice melts. Here, a small lake known as a kettle hole has been formed by the melting of a block of ice stranded in the moraine. meltwater tunnels beneath the glacier become choked with waterborne debris. When the ice sheet melts, it leaves these tunnel deposits as ridges called eskers, which wind away into the distance, marking the former path of the tunnel beneath the ice. But these are small-scale features, and they're rarely preserved as they're often obliterated by subsequent erosion. Meltwaters washing out through the till transport and sort the debris, finally depositing it as stratified fluvio-glacial sediments. Sometimes, as here at the foot of the Athabasca Glacier in Canada, the meltwaters are ponded back by a terminal moraine to form a proglacial lake. During the summer, the meltwater entering the lake carries very fine sediment in suspension, giving the lakes their characteristic milky turquoise color. But during the rush of early spring meltwater, much coarser sediment is washed into the lake. This seasonal repetition of alternate flows of coarse and fine sediment produces an annual banding in the lake sediment known as varves. As well as lake deposits, the meltwaters form braided streams which lay down characteristic deposits in the form of bars of sand and gravel. This region near the state line between North and South Dakota was subject to the most recent glacial advance. When the ice retreated some 10 to 20,000 years ago, it left behind huge areas of till which are still recognizable by their hummocky morainal topography. There's no obvious drainage pattern, and the area contains many small lakes. Some may well be kettle holes. The ground is littered with boulders. Some of these are erratics, originating many hundreds of miles to the north. But the morainal topography comes to an abrupt end. This was the limit of the ice sheet. Beyond a flat area, about 100 miles long and 20 to 30 wide, is the bed of an enormous proglacial lake, Lake Dakota. These lowland features are the result of the most recent glacial advance. Earlier advances of the ice may have left topographic features, but these have long since disappeared. Here, north of London, there's little to indicate that the area was once glaciated. Yet not only can we tell that it was covered with ice, but also that an early advance of the ice diverted the flow of the Thames from this region to the south, where it now flows through the heart of London. This area to the north of London is underlain by sands and gravels. It's from quarries like this that we get our evidence for the diversion of the Thames.
Well, clearly, this dark stuff isn't sand and gravel. It is, in fact, a clay. It's rather dry now, so it's very crumbly, but you can see here where an excavator has cut this smooth groove through it when it was soft and plastic. And it's not a pure clay. Within it are clasts. Here's a couple of clasts of chalk in this block. And if you look around, you can see that there are clasts scattered all the way through it, varying in size up to fist size. And the important thing is they are floating in the clay. Some of the clasts are flint, such as this one. And the surface of it is showing these striations or grooves. Well, all this evidence points to deposition from an ice sheet, the melting out of glacier ice. And it's probable that the flint pebbles and also the chalk pebbles we can see here were derived not too far to the north from here. But up here, there are some pebbles of Jurassic mudstone, Jurassic shale, and I've even been able to find a Jurassic fossil. Here's a belemnite. Now, the outcrops of Jurassic sediments are much further north. They're about 50 or 60 kilometers to the north and northwest of here. So this is pointing to a much larger ice sheet that advanced south onto this area. Now, the till is sandwiched between sands and gravels, so its glacial origin must imply something about the origin of these sands and gravels. Well, the upper ones are better exposed, so let's go and look at them. Well, look at this marvellous cross-bedding. Now, the inclination of this cross-bedding is, of course, giving us the current direction. The current that laid down this particular part of the sands and gravels was flowing in that direction. Now, the face at right angles to this one over there shows a rather different structure. Apparently, a rather trough-shaped pattern is crisscrossing it, but it's exactly the same kind of current bedding viewed at right angles. So there, the current is coming along the axis of those troughs out of the face from the northeast. So it's indicating current flow that way from the northeast. Now, further down this face and lower down in this sequence of gravels, we do again see trough cross bedding. So that's indicating a switch of current direction. Rather than the flow being from the northeast, it's coming probably from roughly the southwest. Above this sequence of sands and gravels occurs yet another till. It's got far more chalky pebbles in it than the lower till, but otherwise the lithology is much the same. So this upper till caps the quarry sequence. Beneath it are the series of sands and gravels, then the lower till, and finally another series of sands and gravels which rest on chalk bedrock. The top surface of the chalk is in effect the valley floor of the ancestral Thames when it flowed to the northeast. So if we look at the current directions recorded in these sediments, we might expect to find evidence of the diversion of the Thames. Measurements have been taken from the lower gravels, and they give a direction flowing from the southwest. And it's possible to measure the flow directions from advancing ice sheets using the orientations of clasts or stones within the till. And the results from the lower till give an ice flow direction from the northwest. So you might expect then, when we come to look at the results, the paleocurrent results from these upper gravels, that this till might have diverted the Thames. But the results don't show that, because the flow seems to have resumed a similar direction. It's changed slightly, it's now from the west-southwest. But what's interesting is, further up in the gravels, the flow has very definitely switched around, and it comes from the northeast. And the flow direction of the ice that deposited the upper till also came from the northeast. So it seems that the advance of this ice sheet was heralded by a switch in the current direction of the gravels. Probably the water that produced these upper gravels was flowing from the ice that produced the upper till. So we now have very definite evidence that the flow direction in the ancestral Thames Valley was switched somewhere in here, within the upper gravels. Interpretation of glacial and fluvioglacial sediments like these allows us to say not only which areas were glaciated, but also how the ice sheets advanced and retreated with time.